Another reason why we have to learn about trap in RISC-V architecture is to gain insight into Linux kernel and real-time operating system. In this lecture, we're going to explore this reason in more detail. If you look into the source code and subsystem of the Linux kernel, you're going to see that the key subsystem of Linux kernel is implemented using exception and the trap. The first example is system call. The system call is interface between user space and the kernel space. But in order to implement system call, the architecture-specific feature is needed. But as for RISC-V architecture, the A-call assembly instruction should be performed to invoke the trap. In other words, the system call can be implemented using the A-call assembly instruction. Right after A-call assembly instruction is performed, the controller is moved to the supervisor mode from user mode. And another feature that is implemented using the feature of the trap in RISC-V architecture is the page fault. The page fault is a mechanism to map the physical frame into the virtual address when the user space wanted to access the virtual memory area. The page fault is taking places with the support of trap. So whenever page fault occurs, the first step is to generate the trap. And the third one is interrupt handling. So many of the key subsystem of Linux kernel is utilizing the interrupt. For example, if you set up the timer in the device driver, a timer interrupt should be needed to get the timer get expired. So interrupt handling in Linux kernel can be implemented using the trap that is supported by RISC-V architecture. Now let's take a look at this diagram to illustrate how the trap is actually implemented in Linux kernel. As you can see in Linux kernel, the trap handler is the handle exception. When the page fault occurs, the program counters move to the trap handler, and then the call to this function, that is to trap load for function, will be called later, and another necessary function to be called to support page fault. When the exception occurs due to memory overload, in this case, this subroutine will be called to print the necessary information at the moment of the memory overload, and then it will cause the kernel panic. So this is the important interface between Linux kernel and RISC-V architecture. This diagram shows you how the user's mode can be interact with the supervisor mode. And if you look at this diagram from Linux kernel perspective, so this is the interface between user space and the kernel space. So if the E-call instruction is performed in the user mode and trap happen, the moving is controlled to the supervisor mode. Before running E-call assembly instruction, the system call number can be specified using A7 register. After controls move to the trap handler in Linux kernel, and then the function call is made to do trap E-call U function. And then inside this function, it will read the system call number using the A7 register. Later, the corresponding system call handler, so system call handler will be called in this step. If the system call is a write system call at this moment, write system call handler will be called in this subroutine. If the read system call happen in the user space, and at this moment, the read system call handler will be called inside this subroutine. All these feature like system call can be implemented using the E-call assembly instruction and the operation of the trap in RISC-V architecture. So if you look into the key subsystem of Linux kernel. Important interface is specific to the CPU architecture. If the Linux kernel is based on RISC-V processor, the critical and important interface is specific to RISC-V architecture. System call, page fault, interrupt handling, all these features can be implemented using the feature of the RISC-V architecture. That is the trap. Now that you got to know the reason why we have to learn about trap. So in the next lecture, we're going to learn about the type of the trap in RISC-V architecture.